Anyone fall in the back parking lot? No? Yeah, me neither. Oh, damn. There's like a flood. Is there no sewage system out there? All right. So, is this too awkwardly close to you? Yeah, okay. Um, so we ended up on this slide, and this slide talks a little bit about magnification. I wanted to point that out here. Before I do that, I want to show you this little angle here, right? We're going to call this the objective angle, right? Because it's the angle in which the incident rays hit the objective. And then we're going to also look at this angle here, which is going to be the angle of the eyepiece, right? And using some fancy math and using the small angle approximation, you get that the magnification is the ratio of those two angles. That's not so important to us. That equation is just an intermediate step to figure out what the actual magnification is based on these two lenses. And then again, for objects that are very, very far away, the magnification of a telescope is really just the ratio of their focal length, of the two focal lengths that make up the telescope. Okay, so we're going to use that equation when we solve the next problem. I want to point out another thing, and that's the way these rays are coming into the first lens. What do you notice about them? They're parallel to each other, exactly. And then parallel rays, we learned, come from very far away objects. And that's what you normally use a telescope to look at. You use a telescope to look at really far away objects. All right. Keep that in mind because it's going to be important. By the way, when you have a parallel object, where do they focus? The rays? They, yeah, they focus at the focal point. All right. We're going to learn how to do one of these problems with the telescope. That's what we're going to do now, actually. So imagine this situation and this situation is the same thing. All right. So you have two lenses. You have the focal length of the objective, which is a really big one, and you have the focal length of the eyepiece, which is a smaller one. And are they trying to come in? They're welcome to come in. You want to just wave them in? Okay, if they come back and look through the window, just wave them in. You need help with that? Ouais, vas-y, rentrez. J'ai déjà fait la maintenant. Oh ouais, vas-y, faites ce que vous. What's that? Why are you here? We're doing a video for all right, so here they're spying on us, this is Big Brother. Um, the um, the important part about this problem is the focal length of the two. Now, we said when you guys were building your telescopes yesterday, you said that, or I told you, and then you found out that it's actually true that you want the focal length difference to be really big. And look at the design here. You have the focal length here of the objective is humongous compared to the focal length of the eyepiece, which is tiny small. And if you look at this equation on the left, you want the numerator to be as big as possible and the denominator to be as small as possible in order to have as big of magnification as you possibly can. Make sense? All right, so let's do that problem, keeping all those things in mind. So we have rays coming in parallel, and that's where we're going to start. And so far, what we drew is all parallel rays coming this way. And it's not necessarily going to be the case this time. All right, the rays aren't always coming from the principal axis. When we're looking at things using our vision, we have rays coming in from our periphery as well as directly in front of us. That term periphery, is that a familiar term for you guys? Periphery, like not our main focus of what we're looking at, but our peripheral vision, like everything around it. So that's the example that we're going to take here because it's going to be more convenient. Well, I'm going to just point out that there's a focal point at this area that's going to be overlapping for the two lenses. All right, so both lenses are going to have their focal point on the exact same spot, and that part is really important. All right, so we have rays coming in. If I have a ray coming in through the center of the lens, what does it do? It goes straight through. So we're going to start off with that. I'm going to have a ray coming straight through. Okay? And every ray coming in parallel to that is going to have to come in straight through as well. So every ray that's coming from a very far distance is going to be parallel as well. Okay? And so they all have to intersect at some point at the focal point, because we know that an image of an infinite object focuses on the focal point. So what I'm going to do is I'm going to refract these rays like that, so that they all meet at the focal point. Okay? And as they're meeting, yeah, Shana? Which rays? Incident or refracted rays? I'm just saying because not everything comes directly from our main vision. It can come from our peripheral vision as well. And that makes this problem easier to solve. Yeah, exactly. The focal point is everywhere along this axis, all right? And we can't go at the point exactly, because if I went right through the center of the lens, right, it would have to be, like I have to go through the lens here, no matter what. For that middle ray, I have to go through the lens no matter what. All right, so that's going to be where my focal point is going to be. So when they're incident, all of them are going to be parallel. When they're refracted, they're all going to be focusing on the focal point because they come from an infinitely far distance. All right. And so that's my primary image that's being formed from my first lens. And we learned yesterday that when you have two lenses, you make the image formed from the first lens, and then you use that image as an object for your second lens. So now, where is this image for my second lens? Where is it located? What's the DO? Where is my DO in this case? My new image, this image here, this yellow arrow that I drew, is located where in front of this second lens with the 10 centimeters, and that happens to be what? That's the focal length. So that's really, really important. You want that image to fall exactly on the focal length of the second lens. All right, and now we have to draw a ray diagram for that. And let's choose a different color. So, whoops, let's go with what's going to show nicely, white. Let's try white. So we have now an object on the focal length, so we know we're going to get what kind of image? This is a trick question, actually. Real? Virtual? Neither. In fact, it's when it's on the focal length, you don't even get an image. You get an infinite image, and we'll see what that means in a second. So let's draw our three rays. So the first one's going to be parallel. And so I guess I need to draw a focal point on this side. And through the focal point, right? I have through the center, and I have through the focal point and parallel. So this one doesn't really exist, but I'm going to draw it anyways. What do you notice about my refractive rays? They're parallel to each other, and do they ever converge? No, they don't. In theory, they don't. In practice, for something to be exactly on the focal point is impossible. So we have to work backwards. We have to work backwards to find out where that image falls. And that image isn't always going to be at infinite. But let's say it is at infinite. What would the magnification be where those parallel lines meet? Is the parallel line going to meet at any point theoretically? What's the definition of a parallel? They do meet, but they meet at infinite, right? So if they meet at infinite, that means that this, where they're going to meet eventually, let's say they meet over here, that's infinitely far. Let's just say, I'm not saying that that's infinite. If they're infinitely far, what's gonna be my image looking like? It's gonna be very big, right? And that's amazing because now, as an observer, I took this really far away object and created this infinitely large image of it for me to look at comfortably. All right. And it doesn't have to be that it lands exactly on the focal point. It could be that it lands just in front of the focal point in here. So let's do a situation where that happens. So I'm going to erase all this so now we can get a concrete image. Right? So let's say my first lens made me an image here. okay? And that's now within the focal point of my second lens, right? And let's draw the ray diagram. So it's going to go like this. That's a good one. This, through the focal point, through the center, through the focal point, and backwards, like that. And so where they meet, if I drew it correctly, they meet there. So I've made a bigger image for myself. The closer I can get that first image to the focal point, the bigger my total magnification is going to be, okay? So now we can figure this out. We can figure out the magnification. We said that it was the focal length of the objective divided by the focal length of the eyepiece. And my magnification in this case is going to be 50 centimeters over 10 centimeters equal to 5. Okay, not a very good telescope, but still pretty good. The closer you are to the focal point, the better it's going to be. So this first image, the one that I drew here with the white arrow, the closer that is to the focal point of the second lens, the better it's going to be. And it would be perfect if it was right on the focal point. Yeah, yeah. The image of the first lens should be on the focal point. Okay? Yeah. You wouldn't necessarily see it because it's not done being formed yet. It would have to be an object that's not at infinite. So an object that's not at infinite won't fall on the focal length, right? It only falls exactly on the focal length if it's at infinite. Nothing is truly at infinite. So if I were to look at, let's say, the building across the street, it's not very far, but it would fall so close to the focal point that you can almost consider it to be on the focal point. All right. Think about this whole situation this way. The first lens, right? I'm going to go back here. The first lens brings the image close, but it makes it small. And the second lens takes that image and blows it up. That's why you have two lenses. All right, you have to bring it close because that object that you're looking at, those stars, or spying on your neighbors or whatever it is, you have to bring that image close to you. Or now, but when you brought it close to you with that big objective lens, you brought it to you close to you, but it was very small, that image. So now you got to take that image and blow it up. So that's why you have your eyepiece lens to make that image bigger. Okay, where can we write that? Let's write that here. So the objective lens brings the object closer, and the eyepiece makes the image larger. Okay. And if you look at it on all of our diagrams, what was the attitude? You guys remember that term, attitude of the image? Is it punk rock? Is it grunge? Is it upside down or right side up? Yeah, the final thing that you see with your eye, is it up? It's upside down. And that makes sense because that's what every one of you guys saw yesterday. Actually, it was funny for me to see that because everyone thought that it was broken. They're like, oh, it doesn't work. And everything's upside down. But I was in my head, I was like, oh, maybe I should have mentioned that. But yeah, it's supposed to be upside down. Yeah, so if you use a telescope to look at the stars, it will be upside down, but you don't notice because when you're looking up, everything is black with like specks in it, right? So when you're moving upwards, it doesn't really change. Or if you're looking at a microscope, for example, you're looking at a cell and there's no up in a cell or down in a cell. So you don't notice that it's actually inverted, but yeah, it's inverted. Binoculars actually have mirrors in them so that they can reflip the image before they enter your eye. Make sense? There's some really cool telescopes that I wanted to go over really quickly. The Hubble telescope uses these mirrors, right? So it's got this huge opening. It's got this huge opening here, right, where all the light from space comes in, right? But because you don't have lenses that are that big, that they don't exist, and you can't make them, or if they do make them, it's super expensive. What they do is they want to converge all of these light rays. So what they do is they put a mirror there, to focus the light on another mirror there, in which case focuses back it down to the center, and that's where the eyepiece is going to be, and that's where you can capture the image. Right? Do you guys, anyone here an amateur photographer, likes to play with like a camera and take pictures? Which guys? These guys? Yeah, so these guys will know that exposure is an actual thing that cameras can do. Exposure is how long do you leave your film exposed to the light, right? And the more you leave it exposed, the more light it's going to capture, and therefore the nicer the picture can be. Our eyes don't have exposure time, right? Which means that we're limited to the amount of light that is given to us in a room. Right? But a camera, you can leave the camera lens open or the camera shutter open, and it'll just keep bringing in more and more light in so that you can visualize things that are really, really dark. Right. So, okay. So now what we can do that our eyes cannot do is take pictures like this. You guys know what this is? This is a nebula. I wonder if it's a stellar nebula or a planetary nebula. It looks like a stellar nebula. So maybe a little bit of backstory on how stars work. Stars have a life cycle, and before they're formed, they're a big amount of gas like this. This is a nebula that's going to be formed into a star, and so it gravitates around like this for a long time until the gravitational pull pulls it all together and creates what is a star. And actually, after the star's life ends, it also ends up looking like this. So it's another stage of the star later on down the line. So it starts off as a planetary nebula, becomes a star, and then in the star's life cycle, if it's big enough, it goes to a supernova, and then you have this stellar nebula. It's beautiful. You cannot see this with your naked eye because one, you don't have the exposure time that a camera does, and two, because this is mostly infrared imagery, and our eyes don't see in the infrared spectrum. And that's pretty cool because we have means of capturing images and rendering them in our own visible spectrum using cameras that operate under the invisible spectrum, right? So you can see UV, you can see infrared, you can see X-rays and gamma rays. Our eyes cannot, but we have cameras that can, and so we use them to our advantage to gain this kind of visual data from outer space and from everything. Like for example, the reason why you guys are able to get X-rays is because we're able to visualize an X-ray somehow, right? Our eyes can't see X-ray because otherwise we'd all be dead from cancer because we'd be X-raying each other. But because we just don't see in that spectrum. We also have radio telescopes that take radio information from outer space and focuses it and uses the same kind of focusing technology. So you have this dish that's going to receive all the radio signal and focus it back onto the captor, which is right there. And that's how we communicate with the Voyager space shuttle. You guys know the Voyager? Yeah, it's the only man-made shuttle that's ever left our solar system. It's the only thing that's in interstellar space. It travels at 30,000 kilometers an hour, which is actually not that fast considering how big our universe is. Right? Sorry, 30,000 kilometers per second. It's not that fast considering how big our galaxy is. It took 30 years just to reach Pluto, and just now it's beyond our galaxy. So how long it's gonna take for it to reach the next solar system? Pretty much never. That's how slow it is. Okay. That's pretty much it. Any questions on this stuff? I'm gonna get into the human eye now. maybe that's more along your things. I see a lot more health science people here. Yeah. Yeah, so let's say we go back. So let's say this is the satellite, right? The radio waves end up coming in like this, and then there's a point here that's attached to the middle of the satellite, and all of these get focused in onto that point in the middle, and that's sent to our computer so we can interpret the data. Yeah. It's like I said yesterday, you want to capture as much data as possible because that's how you can, that's how we could get enough of it, enough information to be able to interpret it. Okay. Which ones? This picture? It sends data. So it's not. It's like radio waves, like you would receive from your car listening to the radio. So it's not. It's not image pictures. It's data. So that data could be translated into images. Like if I were to send you a text message of a picture, I'm sending it to you through radio waves, but the information codes for a picture. Okay. Because it's so far that we don't get enough of it if we just were to get it from just one point. So we need to get it from a big area and focus it all into one point, like funnel. Back to that. Bring um, the optometry slide. It's slide number 13. Nothing. No problem. Go on. Thank you. Did you make me look good? No, I don't know how you said it in French. Huh? Yeah. Bye. So, the area of optometry is deceivingly simple, all right? And you listen to a lot of physicists who are specialists in optics tell you that any monkey can do optometry. So I don't want to be insulting to anyone if their parents or relatives or brothers and sisters are optometrists. But it is, the science behind it is very, 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 very simple. And by the end of this class, or by the end of this section rather, you should be able to go into a optician or optometrist and just tell them what your prescription is and they should give you your glasses. That's how simple this science is. So we're going to talk about how the eye works on its own when it's healthy, and then how we have regular eye impairments, visual impairments that require you to have glasses. I'm not going to talk about like retinoblastoma and those really complicated actual eye diseases. We're really just talking about visual impairments today. So we need to know a little bit about the eye. I put this, I'm sure you have seen it. Did you guys do this in physiology yet? No, not yet. Okay. I don't know if you will, but it seems like something you would do in physiology. It's quite interesting. When I was in high school and all of CJEP and all of my bachelor's undergrad, I wanted to be an ophthalmologist. That was like my primary goal in life. By the way, you know how to spell ophthalmologist? It's the most complicated word to spell. It's like one of the requirements if you want to be one. It's, why does this look so weird? Did I press the wrong button before? No. What's after the P? H. This is where it gets complicated. What's next? What's next? L. Yeah, that's the one that always threw me off. Ophthalmology. That's it should be. The person who looks at eyes is called, and this is actually the medical doctor or the medical science that looks at eye diseases and things like that. Optometrists and opticians are not to be confused with ophthalmologists. This is the one you got to go to med school for. Opticians and optometrists, there is an order for it. It's like dental hygiene and things like that. It's not a medical school. Not that there's anything wrong with it. All right. So what's important for us and what we're going to do today is this ciliary body. All right. I'm going to talk to you guys a little bit about that. The lens is super duper important, obviously, because we're doing optics. The fovea is incredibly important. Do these terms ring a bell? Did you guys ever do this before? Maybe in high school? In French? Okay. What is this term in French? Point noir? No, the opposite of that. This is the one where all the cones and rods. The point noir is here. That's the blind spot. That's this one's what? No? It's the highest concentration of rods and cones. No? I don't know what it is in French. What's this the lens in French? Lentille? No, cornet is this here. Fistale? Okay, so that's the fistale. There you go. And of course, there is the optic nerve that sends the actual potential to your brain. You guys are pros on that now. You got your voltage, gated, potassium channels sending and that. Is that ring a bell? Yeah. All right. So what's important is these ciliary bodies here. And what they do is they're actually attached to the lens. And the lens is actually kind of like a sac filled with fluid, except it's a bit more jelly-like, right? And it is quite rigid, but at the same time, it is very flexible because otherwise you wouldn't be able to focus on close and far objects. What happens is when this muscle pulls on the lens, what's going to happen to the lens? It's going to get narrower or wider? Narrower. Is it going to be more refractive or less refractive? Yeah, it's going to be less refractive. It's going to have you're going to have a thinner lens. So you're going to have a less refractive lens when you pull on the muscles. When you relax the muscles, the cristale, the lens, contracts, and you have a thicker lens, and you're going to have a higher refractive power. Make sense? Right? And so that image needs to be focused on the fovea. Right? And the fovea is where there's the highest concentration of rods and cones. You guys remember those terms? There's cells that interpret the information. Rods interpret light information, so how bright or dark something is, and cones interpret color information, so what color those things are. And so that information gets translated into action potentials, which are then sent through the optic nerve in the cranial nerve 7 into the occipital lobes and the visual cortex. And the brain flips it back around. Right? The refractive index of a lens is 1.406, though that's kind of simplifying it, right? Because it can't be that there's only one refractive index for everyone. It's approximately this. And not to mention that there is a refractive surface here. So just the glass part of your eye, the cornea itself is refractive. And all this is made up of vitreous humor, which is also refractive as well. So I have simplified it by telling you just about the lens, the whole eyeball refractive. Yeah. It's none of it is important. Everything that's important is there. Just for your interest. I won't ask you about how an eye works in terms of the cortex and all that stuff. That's not important for me. So here's a much more physics based question, based information page on the eyeball. So here you have the refractive index of the lens. You can see as it gets towards the edges, it's already changing from the 1.406. What's important here, otherwise, yes, they give you the refractive index of these two, so we're not going to really worry about it. We're going to consider just the lens as a refractive surface. What's also important is this measurement here. All right. So it's going to, like I said before, when you stretch these muscles, right, you're going to get a different refractive index or a different focal point, rather, because it's the same material, than if you were to relax the muscles and have them compress, have the lens compressed. So I want you guys to think about this now, okay? Does your lens need to converge light more when you're looking at an object that's close or far? Why? The rays are not parallel, they're what? If they're not parallel, are they converging or diverging? Your lens converges them, but on their way to your eye, they're diverging, right? So your eye has to work harder to converge diverging rays. Okay? So in that case, your lens is going to be thicker or thinner if you're looking at something close. Sorry? thicker, exactly. Your lens is going to be thicker when you're looking at something close. So that means that your focal length is going to be smaller. All right. And your focal length when you're looking at something that's small, something that's close, is going to be 1.7 centimeters. All right. Your eyeball shape doesn't really change, but your focal length changes a little bit. Okay. And when you're looking at an object that's really far, right? So now the rays are coming in parallel. Your lens doesn't need to work as hard to contract the rays, and therefore it's got a larger focal length, and that focal length is 2.4 centimeters. Okay. So you have a range of focal length. That's a healthy human eye. Yeah. The end doesn't change because the end is determined by the material that it's made out of. You mean talking about from here to here? That's because it's just different regions of the lens. Yeah. So it's a different concentration of stuff. We're going to use this information to solve problems. This is going to be kind of important. I'm never going to ask you to memorize it, but I do ask you to understand the focal length changes based on if you're looking at close or far objects. Okay. I was saying I was always interested in being an ophthalmologist, and then in my second year undergrad, I took this course called Integrative Neuroscience, and it just killed me. It was so hard. It was so hard. I don't know. It was my worst class in undergrad. Anyways. And it was an optional course too. I took it out of interest. It was not required in my program. All right, so here's the problem. So what does the focal length of the lens need to be if an object is located 12 meters in front of your eye? That's like no information. Think about it for just a couple seconds. We'll obviously do it together, but I want you guys to think about it a little bit. What N you use, you don't need an N in this. But you do need a DI. Let's start off with just this. So ideally, where do you want the image to fall? Basically at the back of the eye. So you need to figure out that this here, the distance between the lens and your retina, that's your distance of the image, right? And if the distance of the image is, let's say, 24 millimeters, according to this diagram, you can use that as your image distance. That's an in variable. Your eyeball size doesn't generally change. I mean, obviously, as you're in development, your eyeball does change a little bit. But, once you've reached maturity for your eyes, then they don't really change. So I have 1 over f is equal to 1 over 2.4 centimeters, or rather, let's do this in centimeters, plus 1 over 1,200 centimeters. 1 over f needs to be, or just f rather. You can just give me just what f is. What'd you get? What'd you get? 20? So 2.0 centimeters. You lied? It's not 2.0? Oh, I see. Okay. 2.4, you said? Okay. Yeah. All right, that makes sense. So 12 meters is considered to be relatively far, and at that point, you're already focused on far objects. So if we go back and we look at this, my f far is about 2.4 centimeters. That makes sense, right? Because 12 meters is quite far. If I were to draw something that was much, much closer. So let's do an example where instead of 12 meters, it's 12 centimeters. What does my focal length need to be? Or do what? Let's try. No, that would be the theoretical value. So let's try and see what we get. It should be close to that thing. So 12 centimeters is like this. Your eyes are actually, if you tried and you have healthy eyes, or if you have glasses so that you do look like you have healthy eyes, 12 centimeters away is not a comfortable location for the vision. What'd you get? How much? 2? So closer to the lower end of the spectrum. So yeah, so our eye has that ability, and as you get older, you lose that ability. All right. So there is this something called age-related presbyopia. Have you guys heard of that? Maybe not those terms, but have your parents started doing this with things? Yeah, okay. That is age-related presbyopia, right? It's a form of visual impairment. We're going to talk about it. And what happens is that you lose the ability to contract your lens, right? So you can't see things that are close, right? And so if you can't see things that are close, you're going to want to make them further because you're comfortable with farther objects. All right. So I have some questions for you, and you guys tell me if what might happen to your vision if the axial length is elongated. All right, so that the axial length is that dimension. All right, if that axial length is elongated in your eyeball, what might happen to your vision? Yeah, the image would be in front. So the normally where it needs to focus at the back of your retina, it's going to be focused somewhere in the middle of your eyeball because your eyeball is too long, right? Alternatively, if your eyeball is too short, right, and you have axial length that is shortened, then what happens? Where does the image get formed? Where? Yeah, and behind your eye. All right. And so we need to have corrective situations for that. And the third example I have here is if your ciliary muscles become inactive. So let's say your lens actually hardens and cannot be contracted or elongated, then what happens to your vision? Is it good or not good? Well, it's not good. You need your eyeball to be able to focus on. What I want everyone to do right now is look at your books as close as you can so that you can see a piece of so you can read it still, but it's not like far, right? So for me, it's like this, right? I can see it, and then what I want you guys to do is once you're ready, try to read this word right here. So it takes a couple seconds, not a couple seconds, but it takes a moment for your eye to change their focus from that to this. And the longer you look at your book, right, and switch your vision to looking at this, the harder it's going to be for your eye because it's going to be used to having that lens and that shape. And so making a transition to this is hard. Now imagine you're much older and you've lost control of those muscles that allow your lens to do that shape change. That's what the problem you're going to have. So you're going to have a hard time changing your focus from close range to far range, all right? To the point where sometimes you lose your ability to see the short range altogether. When the length is elongated, yeah, let's just there's the next slide. Yeah. All right, so we're going to talk about myopia first, and this is where your eye is elongated. Axial length is elongated. So what's going to happen is you're going to have your eyeball. We're going to draw it like this. And this is your fovea at the back of your eyeball. I simplified it like crazy, right? Because there's just the lens, there's no cornea or anything like that, but suffice it to say that it all behaves in a similar way. And the term nearsighted means that you can see close things, but not far things, okay? So the problem comes out when you're looking at objects that are far away. So if an object is located far away, the rays that are incident to your lens are going to be what behavior? Parallel, exactly, yeah. So rays are coming in parallel. Let's draw like 5 of them. All right. There's your incident rays. And the lens is going to converge them, but your eyeball is elongated. So normally, your lens, there's nothing wrong with your lens. Your lens is going to converge them as they should, right? Over here, all right? So your lens is over converging. Again, nothing wrong with your lens. It's just that your eyeball is too long, not yours, whoever has myopia. The eyeball is too long. Your lens is working perfectly fine, except it's not being able to converge the light onto the retina, which is further away than it's normally supposed to be. And therefore, what happens is you're going to get this, right? So it's going to cross over, and you're going to form an unresolved picture of the picture behind on your retina. Yeah? So you're going to have blurry vision. Blurry vision for far objects. Okay. So this is the axial length. And that's what myopia is. Just before, I'm gonna have a slide on this later on, but right now, as you're thinking, is a converging or diverging lens going to fix it? Diverging lens, right? So if your eye is over converging, then you need to diverge the rays a little bit so that you can converge them. Okay. Make sense? All right. Let's talk about hyperopia, also referred to as hypermetropia. I don't know why there's two names for this. They're the same thing. And this is referred to as being farsighted. Right? And farsighted means that you can see things that are far away, but you cannot see things that are close. And this is an example of when your axial length is shortened. Axial length shortened. So again, I'm going to draw an eyeball. I have my object there. Or actually, I'm just going to put a dot to make this more simple. So my object is really close to my eye because I'm looking at something close, and it's those close things that I can't see properly. And so I have rays that are diverging like this. And normally, my eye, it would do this totally well, and my lens has no issue. I would converge it onto the back of my retina so that it lands in the fovea and I can have sharp vision. However, this time my eyeball is too short, so my lens isn't strong enough to converge it in time to reach the retina. What's going to happen is you're going to form an image behind the retina. Okay? And of course, there is no physical image behind your retina because your retina is opaque and all that stuff. But the point is, look at the rays that are hitting the retina. So the retina is the back end of your cornea, so right there, right? And so what was a dot as an object now appears as not a dot in your retina. And if that's the case, then you can't resolve a singular sharp object. You're going to see blurry vision again. Blurry vision. So your lens, again, nothing wrong with your lens. It's your eye is too small, right? It couldn't converge it in time. So what kind of glasses do you need, converging or diverging? Converging, right? Because your eyeball couldn't converge it enough, and your lens needs to do some of that converging for you. Okay? And finally, this is age-related presbyopia. This is what your parents get when they get old, what you'll get when you get old too. Age-related. And it's the stiffening of the lens. Right? And generally speaking, it stiffens when that allows you to see far things, but not close things. So is it stiffen elongated, or does it stiffen contracted, the lens? Contracted. Wait, does it? No, the other way. Elongated. Because you can see far away objects when your lens is elongated, but you cannot see close objects. Your lens is, when your lens is elongated, so if you go back, do I have a slide on that actually? Okay. Where did I do that? Here? Forward or backwards? This one? So this is the axial length. This is the eyeball itself that's elongated, not the lens. It, here it's the lens that's elongated. So that's elongated. Stiffening of the lens in the elongated position. Yeah. So in this case, if the lens is elongated, right, it can't converge in time. So if I'm looking at an object that's close, kind of heavy lens. So your lens has lost refractive power, and you cannot converge the rays enough to converge behind the eyeball. You get blurry vision when you're looking at photos. Upstairs at 11. What time does class end? 12:30 or 11:30? 12:30 or 12? Okay, so 12 at 11:30. So we still have a little bit. Are you guys still good to go? Is this getting too long and boring? Yeah. Hyper brighter? Let's see why that might be the case. Um, yeah, I'm not sure about that. Maybe there's. I mean, I'm not a eye doctor or anything like that, but physically speaking, I don't see why. Yeah. And is it true when you take off your glasses? Well, you should. Everyone should always be wearing sunglasses. Okay. I don't know why. Yep. Yes. Um, that's a different ailment. Like if you have cataracts, for example, your lens becomes, the refractive index of your lens increases drastically because it becomes opaque. And there's like a protein that forms inside your lens. Right. So that makes that your lens is not refracting at all properly. So you can't see far and close. But there is no like maybe if you're, oh, okay, so maybe if you're, so yeah, let's say you have hyperopia, right? So so rather you have myopia, so you're nearsighted. No, that wouldn't. So, yeah, so if let's say you're myopic and you're nearsighted, right? And then you develop presbyopia because you're aging, then it's possible that you might need stronger glasses later on. But again, I'm just hypothesizing. Yeah, yeah, that would be like the combination. There are other issues, of course, that are not related to this. This is really like the ray ones that I can discuss in optics course. But there is like there's something called RB protein. Did you guys ever learn about RB? RB is a really important tumor suppressor gene. Did you guys learn about tumor suppressor genes? No? Did you guys learn about P53? Near point and far point. No, just to go back on it, it's quite interesting. There are two genes responsible for all cancers, tumor suppressor genes and oncogenes. There are two families of genes, rather, not two genes. And RB, retinoblastoma, is one of the most important um, tumor suppressor genes that suppresses tumors. So tumors basically are cells that you own, right, that are doing mitosis way too much. That's what a tumor is. And if you have too much mitosis, you have a tumor because cells divided by divide and there's a mass, and that's no good for multiple reasons. And RB is a gene in every single one of your cells, not just in your eye cells. In every single one of your cells, there's a gene called RB that when it sees something that's over mitosing or is doing too much mitosis, it kills that cell. Right? That's your like innate cancer prevention method, except if it becomes mutated, and then you lose that function. So people who have mutations in their RB gene are more susceptible to developing cancer because it's like they call it the guardian of the genome because it protects your cells from over mitosis. There is some infant related cancers called retinoblastoma where they have a tumor in the eye, and that is because they don't express that gene in the eyeball. It's a genetic disease because you're born with it, and it affects young kids. This is different from other cancers because other cancers are ones that you develop over time because your genes become more and more mutated every time they divide, and so you get cancers out later on. This is one's special because it happens more in infants, and it was characterized in infants, and that's why there's this preconception that RB is only expressed in the eyeball, but it's not true. They're expressed ubiquitously in all cells. A little bit of oncology for you there. All right, so we're going to talk about near point and far point. And everyone's got a near point and far point if you have some kind of visual impairment. So if you're farsighted, right, that means there is a point at which your eyes are considered to be looking at something too close. That makes sense? So if you were to, let's say, who's farsighted here? Is there anyone? Yeah. So if Max took off her glasses, right, and I said, you're going to read, take off your glasses. Can you read what it says right here? Okay. That doesn't work. So the test I'm doing is really not the right way to do it, but I'm just going to give you the meaning of the term near point. So can you read what it says in green right there? No? Okay. All right, so your near point is going to be where you can finally see it, okay? In green, sorry. It's not comfortable still. So if it's not comfortable, it's still not good. Okay, so this distance would be considered to be Max's near point, right? It's is it bigger than her? The closest distance is someone who's, no, that's her far. So the furthest distance that she can see far, she can see well. Okay, because beyond this distance, what it's going to be what Max considers to be objects that are far away, right? And closer to this are too close, are close enough for her to read it comfortably, right? So we would describe that distance as the far point, and the opposite would be all true for someone who's nearsighted. So is anyone here nearsighted? Yeah. So you're nearsighted? So take off your glasses. So you can see things that are close, right? So I'm going to come really close, and I'm going to ask you to there. Okay, so tell me when you can no longer read what I'm telling you. You can? Okay, so that would be Marianne's near point. Okay, the distance or that she once it becomes far. So she's nearsighted, she can read things that are near, and and what's considered to be near is going to be that distance measured in meters or centimeters or whatever you want. Okay. The test is harder for the far points because you have to be able to read it from far but not from close. So it's harder to measure that one. Yeah. Again, that was my crappy class test. It's just the idea that I need you guys to understand. The point at which a far object is considered to be far. All right, so knowing that, let's talk a little bit about corrective measures. In myopia, we said that you have an axial elongation. So we're going to write that here, axial elongation. We said that the rays converge behind or in front of the retina. Yeah, converge in front of the retina. So is your lens converging enough or converging too much? The lens is converging too much. And so then you need, sorry, say that again? Correct. I'm not insinuating that either by saying this. I'm just saying that your lens needs to be able to converge the light onto the retina, right? So in this case, it's just not doing that. Okay? And so therefore, if it's not converging it onto the retina, it's doing it in front, you need a divergent or convergent lens. Divergent lens to correct. So let's draw an image now. And we know that a divergent lens is a biconcave lens. There are other examples of divergent lenses. And so you have rays that are coming from that are diverging it so that your lens can converge it onto the back. Make sense? Can you guys do this one? So talk about the same exact things and draw a little diagram. Take like 5 minutes to do it. So I grouped two different impairments for. I can't say that it's axial shortening, or I can't say it's lens stiffening. It doesn't matter. The point is here is that the lens is converging rays behind the retina. So I hope you wrote that. Lens converges rays behind the retina. And if the lens converges rays behind the retina, what kind of corrective lens do you need to have? Corrected using conversion. I'm going to write glasses just to not get confused with the actual human lens. Okay. And let's draw a diagram. So this is how we draw converging lens. So that means that lens is going to do some of the converging for you. It should be parallel here. It should be like this. So here it is. You're watching a close object that has diverging rays or infinite rays because it's really close. They hit the lens converges it for you a little bit, and then your lens itself does the rest of the converging, and it lands perfectly on your retina. Okay? Yeah. The fovea is a place on the retina that has the most amount of rods and cones, or what are those terms called? They're optical cells, I guess. It's what interprets the visual information to a neural signal for your brain. Good. You guys all have, or those of you who have glasses, have some prescription number. And that prescription number is referred to as the power of your lens. And the power of your lens is a super simple term. It's just 1 over the focal point of your lens. Simple as that. So it's I can't make it any more simple than that. Let's say you have -2 glasses, then that means your focal length is -0.5. Yeah, it's diopters. I wrote that poorly. After you write that. Diopter. Meters, yeah. That's a good question. So Max, what is your prescription? Okay, so plus 1.5 you said on one of them? Okay, so plus 1.5 means that it's a converging or diverging lens. It's a converging lens, and it has a focal point of 1 divided by 1.5. So what's 1 divided by 1.5? 0.66? Yeah, so her focal point of her glasses is going to be 0.66 meters. Simple as that. Someone else? Valerie, what are your prescriptions, you know? Oh, okay. So astigmatism is not something I discussed here because that's more of an ailment. Adele, what are your prescriptions? That's big. Okay, so -3 point what? So converging or diverging? Diverging because she has a negative focal point, and her focal length would be 1 over 3 point whatever, which is 0.33. Now, the smaller the focal point, I'm going to get to a question on this in a second, actually, right now. Tell me about this. Which of the following people, A or B, has a greater visual impairment? one that has a far point of 10 or one that has a far point of 5 meters? Why? What is a far point? Can you just define it to me again? It's the point at which you can't see anywhere. So at 5 meters, it's considered to be comfortable. Whereas at 10 meters, so if someone is old and let's say they're looking at something far away. So yeah, you're right. So 5 meters would be the stronger one. If I were to change the question now say A or B, someone who has a lens power of -2 versus a lens power of -4, which one is, what is the question? Greater visual, who has a greater visual impairment, A or B? B. If I were to say another question, A and B, so lens focal point of +6 and a lens focal point of +0.6. +6 has a stronger visual impairment, 0.6. So let's look at that. I wish I have no white marker, but let's say I have these two lenses, right? And one of them has a focal length, let's call these centimeters, meters, doesn't matter, as long as they're the same. You're going to have rays coming in like this, and it's going to focus it on the focal point, right? And the focal point in this case is 6 centimeters. And in the second one, the focal point is 0.6 centimeters. So which one had to converge more? The second one. So that means those are stronger glasses. So that means if you need glasses that converge light more for you, then that means you have a stronger visual impairment. So the answer with this would be okay. Let's try to do this one. Though I'm going to be totally honest with you. I wrote this question this morning, so I'm hoping it works. And I'm hazy on this. So let's give it a try. You guys do it, and I'll try to figure it out on my own, make sure it works. And you let me know if you feel like it doesn't. Ah, okay, makes sense. That's right. It's not an easy question to visualize. But once I tell you the trick for it, I think it's going to make this question and all questions like this super easy. I want you to think about it first. So I'm going to mention one thing. All right. I have a situation where I can comfortably see things at 0.75. That's what the near point is. Okay. So if things are located at 0.75, it's at the height of the visual acuity of that patient, and you want the image to be on your near point. So you need lenses that are going to take an object that are at 25 centimeters and create an image that's at 75 centimeters. Make sense? So if I have a lens, glasses lens rather, and I want to see my book, which is, let's say, here. There's my book. All right. The book is there, but I can't see it properly because it's too close. I'm farsighted, remember? And so I need to create an image that's somewhere right. So this would be your DO or your DI. That would be your DO, because that's the object. And this would be your DI. Is this person farsighted or nearsighted? Farsighted. If they're farsighted, you need diverging or converging lens. Converging lens. So your focal length should be what? Positive or negative? Positive, because it's a converging lens. Is my image here a virtual image or a real image? A virtual image. So the DI should be negative, right? So it should be 1 over negative 0.75 plus 1 over 0.25. So F is equal to? That's good. It's supposed to be a positive focal length, so that's good. So what did you guys get as a focal length? 0.1875? No? 0.375. You guys okay with that? And if that's the focal length of the person's glasses, what is the power? 2.66. The unit is capital D, diopters. So as long as you know what your near point and your far point is, you can easily calculate your the strength of your glasses, and just go to the optician and ask them for that strength instead of paying the optometrist a lot of money to tell you that information. All you need to do is calculate your near point and your far point. I know. And now they're also taking it away for, oh yeah, for you guys and for senior residents. Yeah. Good. Do I have more examples? Oh, yes. Do I have a question on this? Yeah. Okay. So as we know, the focal length of your glasses are quite important. That's what determines your prescription. And your lenses aren't necessarily biconvex, perfectly biconvex, perfectly biconcave. they are a combination of two things. So there is this equation called the Lensmaker's equation, and it's very looks complicated, but really it isn't complicated enough. F is the focal point of your glasses. N is the refractive index of the glass that we use. So in most cases, it's 1.5 or 1.3. 1.5 mostly. This one represents the index of refraction of air, right? But if you're an aquatic being, then this wouldn't be 1, it would be 1.33. Right? None of us are aquatic, and there are no aquatic beings that use glasses. So we just always leave it as 1. And R1 and R2 are the radiuses of curvature of both sides of the glasses. All right, so let's take a look. Here's my lens. I don't know, can you guys see the dotted line here? Not too faint. Maybe you can see it on your screen, or maybe I could draw it here to make it more obvious. Oops, that's not it. That's not the F. So this is one side of the radial curvature of your lens, has a radius, and there's another circle there that makes up the other part of the lens, like that. All right. Can you guys check to see if there's anything over there? Yeah. You're welcome. That's okay. Glasses. Okay. Just a note, if you guys ever miss something, you come after class. You don't disrupt the class. Just a minute. Sorry, go ahead. Because there's air between the goggle and your eyes, so I'm wondering if that's important, or is the outside of the lens important? Good question. I have no idea. I'll have to look at what that means on the equation. Is it the, I thought I'll get back to you though. It's an interesting question. What's important to note is that your lens is made up of two overlapping circles, right? And you can find the radius of curvature for both of them, right? And in this case, the rays are coming in this way, all right? So the eyeball is over here. So I'm just going to draw the eyeball over here, and the same for this diagram, because it matters for convention, all right? If the lens curves away from the eye, the radius is going to be positive. So in this case, R1 is curving away from the eye. You see that? There's the eye, and it's curving away from the eye, whereas R2 is curving towards the eye. So in this case, R1 would be positive, and R2 would be negative. Okay? So here you can say R1, I mean, it's written there, but I'm writing it anyways. R1 is positive, R2 is negative. Okay? And in this case, here are the two radiuses of curvature. And it's first hitting this surface, so that has to be R1. Or the first surface that gets hit is R1. And so there is the radius of curvature here. Is it curving towards the eye or away from the eye in this case? Towards the eye? So is it positive or negative? Curving, so the eye is there, it's curving towards the eye. Positive or negative? Negative. And this one is curving away from the eye, so it'd be positive. So this one would be backwards. R1 would be negative, and R2 would be positive, right? And we define R1 and R2 by which side of the lens is hit first, all right? So I'm not gonna do this with you because I want you guys to have this as practice. Basically, the question I would ask here is, based on all these lenses and the direction, right? You can always assume that the eyeball is here. Determine the signs of R1 and R2 for each of these lenses. is excellent for you guys to practice with when you want to do it later on. The answers are there, but you just don't look at them. The question I have for you is this, and this is going to be my last slide, is determine the focal length of the following. So the formula is 1 over f is equal to n minus 1 times 1 over r1 minus 1 over r2. In meters, yeah. Doesn't have to be. I think if you leave them in centimeters, your answer will be in centimeters, because n doesn't have the unit, and this is going to have the unit of each other because it's addition to subtraction, and they'll be the same unit. So what's the sign of R1? Is it curving away or towards? R1 is the first one that gets hit. Yeah, that's a mistake. On this one? No, look, R1 is the first one that gets hit. R1 is the first one that gets hit. So I guess that's a mistake on the other one. R1. Yeah. Because the R1 is this circle here. Right? So that's the first one of the raised section. In this case, they're both. In this case, they're both curving away from the eye, but it's a matter of which one's R1 and which one's R2. I'm going to say this one's R2 and this one is R1. I think that's a mistake. So the 1.5 minus 1 multiplied by 1 over R1, which is 40, minus 1 over 15. R1 will be, nope, they're both positive in this case because they're both curving away from the eye. So curving away from the eye, and this one curving away from the eye. Is this going to be a diverging or converging lens? Diverging. Someone got a focal point? In centimeters or in meters, it doesn't matter. Minus 48? Does everyone agree with that? Just looking at this lens, you should be able to tell if it's going to be a converging or diverging. Why? Which ones, this end is going to converge or diverge? This looks more like a biconvex lens, right? So it's the convex part of the biconvex, so that's going to converge. This one's going to diverge, but which one's got the sharper radius of curvature? This one, right? So this one's going to just going to emporter over the other one. It's going to win over that one because it's kind of sharper. So overall, it's going to diverge. That's it. All right. Let's take a 7-minute break and meet upstairs in the bio lab, okay? Bring your lab coats. An hour and a half. I'm sorry to have to done that for you.